We're about to have fun in this course. Maybe not today, unfortunately. But we will at some point, I promise. We have spent the past 3 weeks talking about server-side scripting and talking about specifically Razor pages. And we went over a couple of examples, and we saw how you have those two files, the CSS_HTML file and the .cs file, and those together form the Razor page. The CSS_HTML contains most of the static HTML and a few little script tags here and there. Most of the work of coding-wise occurs in the CSS_HTML.cs file. And the model, as it is called, is noted on the CSS_HTML page, and therefore that associates the model with the particular page. Do you have any questions on how that works? Do you have any questions about your homework assignment? No? Okay. Well, then, the reason I said we're going to have fun is because we're going to start covering database stuff. All right. The name of this class is Web Database Integration. And that's sort of an outline of how this course works. First few weeks, we do the web part. Second few weeks, we do the database part. And then the rest of the semester, we do the integration part. We connect the two together. All right. So what I want to do is I want to go through an exercise, or I want to first ask you, this is a good idea. Let's sort of brainstorm. And let's think all of the things that we can think about databases, either defining or describing a database or part of it. What do we know about databases? Yes. Okay, very good. There is in each table contains or should contain a primary key. And that key identifies one specific row. They are unique, in other words. So if you have student ID as your primary key in the student table, there can't be two students that have the same student ID. In addition, there cannot be a student that does not have a student ID. If they do not have a student ID assigned yet, you can't leave it blank. You can't have it as a null. You have to have a value in it. So that's characteristics of a primary key. Two of the characteristics of a primary key: must be unique and must be not null. There has to be a value for it. Let's back up a second. And what does a table represent? Yep. A table contains all the data about a given entity. So for example, if we have a student table, everything that's an attribute of the student will be in that table. You will not have, for example, the student's email address in some other table, in an enrollment table or something like that. All right. So A table, to define a table is a representation of an entity. An entity is, again, sort of a noun in our problem domain. So if we were going to have a database for a store, there might be a table for departments that would list all departments. There would be a table for products. There might be a table for employees. There might be a table that assigns employees to departments, and so on and so forth. Okay? So all the data about a given entity is stored in a table. What's the key difference between storing data in a database versus storing data in a plain old file? You want to take a stab? Okay. The question was what's the difference between just putting the data in a file as opposed to a database? And the answer was the organization. There's a lack of organization with the plain old file, and that's definitely true. There also is not one other important thing that we store in databases that we do not store in plain old files. Anyone care to take a stab at that? And that is the relationships between the data is stored. So going back to our store example, all right, the relationship between employee and department. There is a relationship. Employees work in a department. Can an employee work in only one department? I don't know. Depends on the store. Maybe in some stores they can. Maybe in some stores they're not allowed to. Maybe in some stores they're assigned to a department and they can be loaned out temporarily to another department, but they're still considered a member of the first department. Or maybe an employee can be part of multiple departments. Products and departments. Is it that every product is assigned to a given department? Or do you have some things that might be in multiple departments? Let me think of an example. Snow shovels. All right. Snow shovels might be in the house department, the household goods department, and they might also be in the automobile department, because it's probably a good idea to have a snow shovel in your automobile at times. So you might put, that might be how it is, or maybe the way your store is organized, nope, every product is only in one department. When you're developing a database, you have to find out these things, and you go through a process in finding out those things. But the bottom line is, regardless of what the specific relationships are, the relationships are actually stored along with the data. If you have files like a plain old Excel spreadsheet, and you had a student file and a professor file, there really wouldn't be an easy way to link the two files together. I hesitate to say you wouldn't be able to, but there wouldn't be an easy way to. All right. Whereas with databases, those relationships become part of the package. Well, they become part of the package if you design your database correctly. All right. And we'll spend some time talking about that today. Associated with relationships is the notion of a foreign key. A foreign key is when you have a primary key of a table stored as a piece of data in another table. Let me give you an example. Here at the college, I'm assigned to one department and one department only. So there might be a row in the faculty table that has my name. Maybe employee number 83759 is Mike Zellers. All right. There then might be a list of departments. All right, where department 1 is health services, department 2 is enrollment, department 3 is registration. Department 4 is engineering, business, and IT, my department. So the primary key to that is 4. In other words, to have a foreign key, you would store the 4, the department ID, in my employee record. That way, my employee record would not have all the data from the department, but it would point to the department. And that's a key point to make, pardon the pun, is that you have data pointing to each other. And that's done through the use of foreign keys. Now, simply by having the data doesn't make it so. You have to define the foreign key for it to work correctly. We talked about primary keys. All right, we said a primary key has to have 2 characteristics. Number 1 is that every member of that entity has to have a value for it. So you can't have a student without a student number, for example. Well, that's fine. We can control that, right? When we enroll, when a student applies for admission to a college and we put them in the student database, we can generate a student number for them. So we got that handled. And also, that has to be unique. Well, we got that handled too, because we'll make sure that when we assign it, that we're not assigning something that someone else has. And again, you're not going to run out of numbers. Right? So if you're using a numeric primary key, it's going to take a lot of data, and even then you'll still have numbers to spare. What makes for better primary keys, do you think? Numbers or text string? For example, would student be a better primary key than email address, or would email address be a better primary key than student number? Student number would be a better one. I believe that. I agree with you. Why? How did you come to that decision? Yeah, that's pretty. In other words, for everything that you do on campus, your student numbers involved. Could you make it the email? Yeah, but that doesn't seem to be quite as concise. A couple things about email address. You might be able to change your email address. All right. Does every student have an email address? Yes, they do. All right. Because again, like the student number, as soon as someone is enrolled in the college, they get generated an email address. A couple other things. The data you can store in a numeric field is much more concise than the data that you can store in a string field. All right. For example, in 2 bytes of data, let me do the math right. In 2 bytes of data, there are 65,000 possibilities. If we bump it up to 4 bytes of data, you're up to 4 billion. So yeah, 4 bytes of data will store 4 billion students. Pretty safe bet you're not going to run out of student numbers. And you know that that could take only 4 bytes to store in the database. Let's see what we could store if we use characters. I'm going to estimate there are I'm going to estimate there are 42 typable characters on the keyboard. That's only 3 million. All right, 3 million combinations. And if you restrict to only alphabetical characters, like for example, if you had a student name, for example, as a primary key, then you have even less with 4 bytes. It would be 26 times, which would be 500,000, all right, compared to 4 billion. Big difference. So numbers are often a good idea because you can store them more concisely. And that matters, all right? That matters because we're not going to store the primary key just in the main table. We're going to store it in all the related tables too. All right? So the department ID, if that is a string and it's 40 characters long, that's 40 bytes we have to store for every professor here on campus and every employee on campus. That's a lot of data. That takes up a significant amount of data. If, however, we use a department number, then that's maybe only 2 bytes, because 2 bytes you can store 65,000 and change, all right? So you can store it much more concisely using a numeric field than an alphabetic field. And again, that adds up because of the idea of the foreign key that we have related data. The other thing to be very careful for is when people create a key is to be sure it is unique. Unique doesn't mean unique most of the time, all right? It means unique all of the time. So, for example, last name. That's obviously not good. 2 people can have the same last name. First name and last name. That's not good either. First name, middle initial, and last name. Could still happen that you get 2 people with that. First name, last name, first name, middle initial, last name, and their birthday. Wow, the odds would be slim, but not impossible, right? That you could have 2 people that were identical to that. And you don't want your database to break. If it's to be unique, if it's to be a primary key, you want to guarantee that that field is going to be unique. And you can easily control that if you use a number as the key, all right? Another problem that you get into is changing a primary key. Depending on the database, changing a primary key can be problematic. It's going to be much more difficult to change a primary key. In the example I gave, where each department gets a number, the numbers I assigned are arbitrary. Doesn't matter that engineering, business, and IT are department number 4. They could have been department number 12 or whatever. That key has no real meaning outside of the database. That is what's called a surrogate key, all right? And those never are going to change. If you use something like a department name, well, we've changed already since I've been here. We used to have a business division and an engineering division. Now we have engineering, business, and IT division. So you'd have to change that. And again, if that were the primary key, you'd have to change it not just in the table itself, but in all the tables that are related to that department, which would be a much bigger task. All right. What is a normalization? What is database normalization and the rules for database normalization? You don't have to spot out the rules, just tell me what the purpose of normalization is. Okay, the statement was made that you take the data that you have in a database and you break it up into pieces. You don't store all the data into one table, but you create separate tables for different related pieces of data. And in doing so, you can remove some data that you don't really need. All right. That's a really good definition. All right. My definition of normalization would be similar to that. But I would say normalization is the process that you go through, all right, to make sure that every field in a database table can be uniquely identified by the primary key, and only the primary key. Let me give you a for instance. All right. Let's say we stored department name along with department number in the faculty table. The department name isn't needed, right? Because that doesn't depend on which faculty member you're talking about. It's not as though when you're talking to Zellers that he is in the engineering, business, and IT. When you talk to Neelan, he's in the business, IT, and engineering, and so on. All right. So in other words, the name of the department doesn't depend on which faculty member you're talking to. I'm going to call it by the same name as Neelan will, and Huber, and so on. All right. In other words, it doesn't depend on the faculty member you're talking to. It doesn't depend on the primary key, which faculty member you're talking about. It does depend on the department ID that you're talking about. Department 4 better be engineering, business, and IT for everyone. All right, that makes sense. There's only one place to change the name if you need to change it. All right, give me the department ID and I can tell you precisely the name of the department with no ambiguity. All right, no saying, hey, that isn't a valid ID. Give an ID, there's an association between the ID and the fields in the table. So I have this exercise that we will work through together. All right, there's actually normalization rules. And if you are in CISS243, you probably learned them. All right, I would hope you learned them. All right, I'm less concerned about the words of the rules than what the rules really mean in action. In other words, how we're going to use those rules. Now, this is a hypothetical situation, but it's a sort of realistic one. All right. Oftentimes, before a particular area of a business is part of the system, people had or will or currently have spreadsheets containing the data. All right. And with spreadsheets, those are just plain old files. Data isn't related. So they might have a spreadsheet like this for the computers that are on campus. I just did 4 of them because we can get the idea. Computer 1 is in the BU building. What is the BU building again? Oh, that's the business building. What room? Room 106. What's the name of the room or the description of the room? It is an open lab. What year did we purchase it? 2020. What applications are installed on it? And for simplicity, I only considered 3 applications. All right, obviously you'd have more, but I considered 3 applications that are stored in it. This is such an old example that I've used for ages because this part of database theory has not changed for a long time. All right, I had to update the dates because it said like year purchase 2002 and software Macromedia Flash. All right, so I was frantically doing that before the class began. I don't know if it got recorded or not. I think it got broadcast there, and you could have saw it if you were watching. Now, this is one scenario. Typically, you'll build a database a couple different ways. One way is you will look at the source documents people have. So in other words, if you wanted to create a database for this information, you'd ask people, how are you doing it now? What forms do you use? And they probably would show you this spreadsheet. All right. Or you might talk to someone if it was a brand new venture, and you might talk to someone and ask them to describe the entities that exist in the problem that they're trying to solve. All right. And what information the database needs to store. And you might take a shot at defining some tables. In either case, you might start out with one table, you might start off with a rough draft of several tables, but in any case, you go through the process of normalization to make sure that your tables are spot on. Another way to say that is to make sure that the data depends only on the primary key. First normalization rule. And we'll talk about the rules, but we'll focus on what they mean. First normalization rule says every table has a primary key, and there are no repeating fields. Are there any repeating fields in this table? Absolutely is. Which one? The application codes. We have 3 spots for application. Application 1, application 2, application number 3. So essentially you have the same fields, but 3 copies of them. Okay? I think we can see why that's a bad idea. That's a bad idea for one reason, is not every computer in this case would have 3 applications. Again, assuming the arbitrary number of 3. You can say X number of applications. And you're kind of going to be wasting space for all the extra ones. The other problem with it is, what if a computer has the 4th application? You can't put it in a database, and your database design breaks. All right. I talked about this in a little bit in CISS243 this morning, but a big factor in any software design you use, whether it be developing JavaScript code, developing databases, writing C# code, and so on, is developing systems that can handle change. All right. And it's easier to change data than it is to change database structure. Right? Remember that. It's easier to change data than database structure. All right. So, first thing we're going to do is we're going to get rid of these repeating fields. So they're gone. All right. Actually, let's put them on this page too. I hate that when you copy it, makes you copy it again. Does anyhow. What am I doing wrong? There we go. Okay. We'll put this in here just so that we remember the data that was in here. So what do you do with these repeating fields? Well, the answer is almost the same for every bad situation that you find in database design. You create a new table for it. All right. So we will create our application table. By the way, one of our goals in doing this normalization process is we don't just want to change the database structure. We have to keep all the meaning, all the information that was in the original. So one thing we can do is we can create a application table. I'm going to put it off to the side, at least for now. Application ID. I'm practicing what I preached here because I'm going to make it a number. So application 1 we'll say is MS Office. Number 2, VSC, Visual Studio Code. Three is Android Studio. Number 4 is Visual Studio. And number 5 or NetBeans. So what did I do? I found all the unique occurrences in that table. Not that table, in those columns. I found all the unique occurrences of the application name and so on. Now, if we need to change something, there's only one place we need to change it. If, let's say, we had a new hire and they spelled office wrong for whatever reason, or they didn't understand, we'll make a more realistic one. They didn't understand the word Visual Studio Code. And so they typed in Visual Studio Code or something like that, a help service for students that are working with Visual Studio. And they typed in Visual Studio Code. Well, if you need to change it before, you'd have to find all the computers that had it and change it. And it could be in spot number 1, it could be in spot number 2, or it could be spot number 3. So here, if you spell the name wrong, you'd only need to change it in one place. So we can get rid of this data now. Maybe. There we go. I'm going to make this a little bit bigger. And I'm going to make it so that it is center aligned. All right. We have a problem now. What is our problem now? If we left it at this, we'd have a problem. What is our problem? Two tables aren't linked. In other words, we lost a piece of information. We got rid of the redundancy of having the application in the table a bunch of times, but now there's no way to associate the application and the computer. So we'd have to go back and we'd have to put in the relationship. And we can do that by, first of all, determining the kind of relationship. And that is known as the cardinality of the relationship. 3 kinds of cardinality, and one is the main one, all right? There's one-to-one relationships. Those are actually pretty rare. It's actually very difficult to think of a one-to-one relationship. The best one I've come up with is the relationship between a dean and a division. Every division has one dean, and each dean is only dean of one division. So that's the best example I can think of for a one-to-one. There's one-to-many, which means that one computer can have many applications, or one application can be on many computers. Or lastly, there's a many-to-many relationship. Here's the thing about many-to-many relationships. We have to break them down. We have to break them down into 2 one-to-many relationships. Now, a couple things we cannot do. I can't put an application ID in the computer table. Why not? Well, because a computer can have multiple applications, right? So I couldn't put a single application ID. What about putting a second or a third? Well, that's what got us into trouble in the first place. No, we can't do it. What about putting in a computer number on the application? Well, we can't do that because each application can be on multiple computers. And same thing about having different slots for computers. So we come up with what's called an intersecting table. And we do this a little bit different. We're going to have a table that connects those 2 things together. So this is what I'm using the other tab for. First computer has Office and Visual Studio Code. So computer 1 has Office and Visual Studio Code. Second computer has Office, Android Studio, and Visual Studio. Office, Android Studio, and Visual Studio. Finally, computer 3 has NetBeans and MS Office. And lastly, computer 4 only has Microsoft Office. Now we have recreated that structure, all right? We've recreated that information. So if I know a computer, if we went back and looked at the original spreadsheet, which I wish I would have copied to another tab, instead of just that one section, if we look at a computer, we can tell the applications are on it. I want computer 1. Well, it has application 1, which is Microsoft Office, application 2, which is Visual Studio Code. Now, to the point I had before, if something was spelled wrong, let's say we omitted, we got rid of the space between Microsoft and Office. Previously, you would have to go and change every occurrence of that. Here, we only have to change the 1. Now, there's a problem, or not a problem, there's a question. What is the primary key to this table? Can it be application ID? No, it can't because we have duplicate values. Can it be computer ID? Can't be that either. So it has to be the combination. And I usually, when I'm writing things, I put an asterisk next to the primary key of each table. And I put a double asterisk next to something that's a foreign key. So this is both a primary key and a foreign key. Okay, so that cleaned it up quite a bit, right? Now, foreign keys enforce what's called referential integrity. What does that mean? It means that I cannot say the computer 4 has software number 7. Why? Because there is no matching software number 7 in this table. Therefore, this would not be allowed. And it's not allowed on the database level. That's really important. You want to enforce as many rules as you can on the database level, because then any application that accesses those, the rules apply. If I enforce rules in a program, the rules will work within my program, but if someone else writes another program or a mobile application or a web application to maintain the same data, they would also have to get the rules right in order for the data to have integrity. Well, that's a risk. Right? And you know eventually you're going to have things that point to things that don't exist. Well, with the database and referential integrity, that is implemented in the database, and the database is sort of the gatekeeper into any data that's trying to go into it. So the rules will be enforced. Now, what other thing do we have here? Well, we have a problem. Building code and building name. What if they rename the business building to the M. Zeller's business building? You have to change it in 4 places. And correspondingly, they change the code. Well, that's obviously not good. The name of the building doesn't depend on which computer you're talking to. In other words, this computer is named the business building, but one of those computers in lab is called the business and technology building. No. For every computer, it's the same building. Therefore, we can separate this out. And again, I'm going to put a building ID that's going to be my primary key. And I'm going to put the building code and finally the building name. Here, I only have one of them. We get rid of these 2 fields. Brush up on my cell. We get rid of these fields. No, not that. Okay. Now again, we've lost information. What information have we lost? We've lost the fact that computer 1 is in the business building, computer 2 is in the business building, and so on. How do we fix this? What's the kind of relationship between between building and computer? Is it 1-to-1, 1-to-many, or many-to-many? Well, we know it's not 1-to-1, right? Because this campus has multiple computers, or this building has multiple computers. So we know that one building can have multiple computers. Can a computer be in multiple buildings at the same time? No. It's important when you check a relationship that you look going in both directions. Because if I only looked in one direction, I could say, yeah, a computer has multiple applications. I think it's a one-to-many relationship. When you realize, no, that's not the case, we need to check both ways and say that the application can be on many computers. We fix that with a foreign key. Put the building ID. So essentially what we're doing is we're taking out data that doesn't depend on the computer, the specific computer. We're making a known table about it, but we're verifying that the relationships are still contained there. Don't lose any data. Last one is the room, and I think we can see read the writing on the wall. So we have in room ID of 1 has a building of 1, and the room number is 106. Building room number ID of 2 has a building of 1, and it's room 210. Well, again, we've lost that association. Therefore, we have to put the room ID in here. Now here's something nifty. If we know the room, we know the building. So we actually don't need this building ID. That's sort of a rule in database design. Yeah, there's a relationship between computer and building, but we don't have to implement it. There's what are called derived relationships. And this is an example of a derived relationship. There's a relationship between computer and room, but you get to that, or I'm sorry, between computer and building, yeah, because the building has computers in it. But you get that relationship by going through the room. As long as you can get there from here, that's all that matters. All right. So this would be the completely normalized, I think, looking at this. Yes, this will be the completely normalized version of this. We know what room it's in, and therefore we know what building it's in. We know what applications each computer has. And everything's a neat little entity. We broke it out, and as you said, it's organized properly. It's organized into entities, and we still maintain the relationship between them. Any question? Yes. This one? Oh, you're right. You're right. No, we would not. In fact, we wouldn't want that because, again, that could lead to inaccuracies. There's one problem with this. aghast. I missed something. What did I miss? Well, the room ID depends on the computer in. The room description, does that depend on what computer? No. So this should be gone too. And we should put a room description in the room table. Now, are there any questions? All right. Announcement, there will not be class next Tuesday. I will probably have an activity for you to do, or I'll have another lecture that I'll cover more details. I'll either pre-record a lecture or I will have an activity for you to complete. So next Tuesday, no class. I hope, knock on wood, that that's the only Tuesday after this. All right, question.